Good morning to people in India. And My name is Siddhartha Dalal, and my collaborators are Zihe Wang and Siddhanth Sabharwal, who is actually on Zoom right now. And welcome to you all. So as you know, ransomware has become a very big deal lately, but it has been around for a while. And the question is that and typically ransomware is collected usually on Bitcoin network. And so the question is, can we identify actors which are responsible for asking for ransom? And that's the question which we are going to discuss today. And of course, ransomware attacks have been all over in US and around the world. And in fact, just recently, there was almost $10 million payout for attack on a pipeline company, a gas pipeline company. So you can imagine the amount of impact it had across a variety of places around the world itself. So what is ransomware? Ransomware is nothing but cyber criminals use malicious software code to block people or organizations from accessing their computer systems until a ransom is paid. The ransom is typically paid in Bitcoin because Bitcoin has got pseudo-anonymity, and therefore, due to pseudo-anonymity of the actors on the platform, uh, the actors are protected and they can transfer money very, very quickly. And in fact, it turns out that Bitcoin has accounted for large amount of ransom. For example, between 2012 and 2017 alone, more than $1 billion were transferred over Bitcoin network for ransomware. And there are various kinds of ransom where basically it gives in some there are crypto locker, WannaCry, and there are many other different types of that. Basically, they lock up the screen or they lock up the system, they encrypt the system, and if you don't pay them, then system can destroy by itself and so on. So there are various ways of doing it, and we won't go into the detail of it. We want to understand that from the network of Bitcoin, to what extent can we identify ransomware actor here itself. So I want to just point out quickly, here is a picture of the Bitcoin network where you have blocks and each of the block is carrying a data and so on and so forth. And typically they are transactions. Transactions are from some address which is on Bitcoin network to another address. So a victim will pay to a person or an address which is demanding ransom, and basically those transactions are being recorded, and transactions are recorded in a type of script itself, and scripts are binary and not human readable. So we used parser called BlockSci to basically convert it in human readable form, which can be processed in terms of our software itself. Given that, now let's talk a little bit about what kind of bad actors we are looking. Actually, we generalize our problem beyond ransomware to bad actors, and we basically looked at two sets of it. One is the people who were responsible for ransom collection, ransom attack, and so on, and the other one was gambling. People who are gambling on site on network. Typically, they tend to use uh, basically Bitcoins to launder the money often. And so many of the gambling sites are used mainly for laundering money itself. So we were interested in really trying to identify both of these kind of actors. And as a comparison group, we took a random sample of addresses and we called them as random. And ultimately, we compare all three of them. And we converted this problem in terms of supervised learning. And I won't go into the detail. Much of these details are already in the paper, which you all have. But we collected ransomware addresses, basically where victims were reporting afterwards, after the attack, that here is an address which demanded ransom from me. And a lot of those addresses were already in variety of places, including Bitcoin Who is Who, Bitcoin abuse, and variety of other literature itself. And we looked at, similarly, we collected gambling, where we looked at gambling sites and people who were connected to them, and we found their addresses. So that's the way we started all of this, basically starting with addresses themselves. And we created first transaction graph. So let me just mention quickly about transaction graph. Here is a transaction where there is input addresses with some amount of money from each of the input. And finally, there are output addresses and some amount of money which is going to output addresses. These are nothing but sats here. So it won't tell you exactly how much money from here is going to here. It just is telling you how much is the output and how much is the input from here itself. And obviously here now we have got two addresses. They might spawn their own transaction. So here is another transaction, here is another transaction, and we can go on transaction after transaction, and we can go on building it. So here is an example of transactions for one particular actor, which was actually involved in ransomware. And as you can see, we looked at only 1,000 transactions. We wanted to just show you how the picture looked like. And as you can see, some of them are going to the places which have got lots of connections, and some of them are really very tiny connections. And so they all have different kind of network here. And what we are trying to do is trying to identify structure of this graphs, transaction graphs, and actually related graphs we'll call as actor-to-actor graph, and ultimately select which one are likely to be ransomware actor. And we created an algorithm basically to look at, create the transaction graphs of the types I mentioned here. And we basically looked at only plus or minus 1 day of a reported case of ransomware where ransom was demanded, and we looked at the address, and we looked at basically the transaction involving that actor, and we basically went through where the money came from, where money is going, and we go on iteratively looking through the whole thing, and that's created the whole transaction graph. A transaction graph consists of basically vertexes, which are nothing but transaction. The edges are nothing but addresses, and money being transferred is nothing but the weights. So that's the way the whole transaction graph was created. So here is an example of a transaction graph, which I just showed you earlier. Now, there are various kinds of transactions which are rather complex, and I would just mention quickly those kind of transactions which needed to be spatially taken care of. And those are the ones which are what are known as coin-based transactions which are nothing but getting algorithmic input for miners. So anytime somebody mines a block, then automatically algorithm would pay now 6.25 Bitcoin. And so those are the kind of things which are called coin-based. So there is no input directly from somewhere else. It just is directly generated from the chest of Bitcoin. There are also other kind of addresses which are involved in transactions called change address. And change address are the ones which are completely new addresses which have been created and likely to be used by one of the input address for anonymity reasons. Then we also stopped transactions which are going to exchanges or gambling sites, because once you go to an exchange, then exchanges are connected to so many people that they're not likely to be very useful to follow those. We also looked at proof of burn, which are nothing but addresses which are actually putting some data on Bitcoin network, and they're burning their Bitcoin. Now, right now it doesn't happen much, but it was very, very common practice to store certain data on blockchain. Now, there are scripts. We looked at a script I showed you earlier. There are non-standard scripts which are not, the language which is used in terms of Bitcoin is a limited language, but it's got something like around 76 different operands. But some of the transactions are rarely used at all. So many of the parser would not parse those. So we needed to create a special way of handling those kind of things. And finally, one of the most difficult part was what is known as identifying what are known as coin join transactions. So coin join transaction, typically one would be able to have addresses which are going to another set of addresses, and typically one would be able to identify who is paying whom in a variety of ways. The coin join is a very clever technique by which involves multiple independent parties transacting together through an algorithm or through actually another service which are available today, which will match roughly same amount of Bitcoin on input side and output side. So one would not really know who is getting from whom the money, because they're after all nothing but a set of transactions. And there is no direct connection between one side to the other side. There is no way to map it. So those are coin join transactions, which are commonly used for, and which were rare, but now they're more often used. And those are the ones which are which creates a lot of problem in terms of identifying addresses. So these are all the ones which we had to tag itself. Let me continue here now. So now we needed to remember we have an address, but every actor can have thousands, possibly millions of possible addresses. You can create addresses on fly itself in Bitcoin. So we really are not interested in here is the particular address which is responsible for ransomware. We are interested in the whole entity who is one, who has got many addresses, and we want to identify the actor, and we can identify actor by looking at the collection of the addresses that the actor is having. So we needed to basically start and create, instead of address to address graph, from transaction to transaction graph, we decided we needed to create actor to actor graph. And actor is nothing but a collection of addresses itself. So there are various, so we had to cluster that given the addresses are there, we needed to cluster them together in terms of here are all the addresses belonging to the same actor. So there are heuristic algorithms which have been developed for this part of it. And there are various heuristic algorithms which have been created. One of them is very simplest ones are like if there are inputs, multiple inputs to a particular transaction, then they're likely to be controlled by same actor. And so let's put them in a cluster. Obviously that goes into trouble if you're coin join transaction. And then if there is a new address, which is an output, then in that particular case, chances are high that it would belong to the input set itself. So you combine them. So there have been several transactions, several such things which have been created, and the clustering algorithms have been created. Now, there are a lot of difficulties with this global algorithm, which start all the way from initial block, which is called Genesis block, up to the AND itself. And in fact, it turns out that when you do clustering using this kind of algorithms, then you tend to get huge cluster. Like one of the reported study had one cluster had 98% of the addresses. And so you're talking about like almost out of 400 million addresses, 98% of them belong to one cluster, which is very unlikely. And it's likely to happen because of the failure of this kind of algorithm. So we decided that we should not have a global clustering. We should have actually instead should have local clustering. And local clustering idea is very simple. It will just look at a transaction within plus or minus 1 day, of the initial reporting of the address, which is ransomware. And we will just look and cluster within that thing, taking into account coin join itself. The great advantage of that is that we get very local behavior, and that's an advantage because most of the time ransomware actors, they move money very quickly. Once they get the money, they want to turn over to another account, to another account, to another address, to another address, to another address. So we are able to capture that very quickly. And there is much smaller chance of false positives. And so that was the main reason that we adopted this approach. I won't go into the detail of the algorithm, but the algorithm is being discussed in the paper very, very carefully here itself. Now we get now, so we cluster now. So we have now basically actor to actor graphs themselves. And now we are trying to look at actor to actor graph, and we break it up in terms of different kind of data sets out of it. So actor to actor graph, you can have you can have multiplicity, same because the actor can have multiple addresses. So and a cluster can have up to 100,000 addresses, or a particular actor can have up to 100,000 addresses, and they're going within itself. So there are multiplicity as well as there are loops which are there. So simple graphs are nothing but we remove the loops. And then we basically look at ego graphs. Ego graphs are the ones which are, ego graph order 1 is nothing but clusters which are only distance 1 away. And ego graph of order k is nothing but distance k away. So we are basically looking at ego graph up to order 3 itself. And then we try to measure variety of centrality parameters of this graph. So we get this huge graph, which can be, as you will see shortly, up to 500,000 to 1 million potential nodes and vertices, and more than 1 million edges. So we look at variety of number of vertices, number of edges. We look at degree, closeness, betweenness, page rank, neighborhood size, coreness, and cluster coefficient. So let me just show you a little bit of data, and I wanted to just describe to you a little bit about what the features look like and what is the differences. So what we have here is what are known as Boxen plots. They're very, very similar to box plots, but they have got more quantiles, which are drawn here, unlike box plots. So if you look at this particular chart, this is nothing but number of vertices, and this is nothing but number of edges of each of the ransomware actor, which had been identified. And as you can see, that ransomware actor here has got transactions where it has got actually number of addresses in this particular graph within plus or minus 1 day is more close to more than 100,000, 10 to the power 5. And number of edges are like nothing but 1 million. And as you can see, that number of vertices here are far larger because most of the ransomware actor are having very quick, complicated turnaround, and consequently they're using lots of vertexes. They're constantly moving, shuffling money very, very quickly so that nobody can trace them, or it would be hard to trace them. And therefore theirs are the highest one. And gamblers are also doing same thing. They are laundering with the money. So they're moving a lot of money around. And as you can see, and these are nothing but the people who are comparison group. Same issue arises in terms of edges, which are nothing but proportional to more or less vertexes. I'm sure many of you know about PageRank. PageRank is nothing but a way for measuring, usually for websites, which is a more authoritative website. And the way to think about it is the more input you have, the more reputation you have, and consequently you have got higher PageRank. And so if you look at it in terms of PageRank for the ransom graph is much higher compared to random and gambling graphs. And the reason being that a lot of people are being asked to send their ransom payment. And so consequently, they tend to have a lot more input, and output are going to only some addresses, and they're constantly moving out to other addresses. Consequently, their page rank is much higher. And if you see gamblers are basically working within their own network, small number of network, and therefore their page rank is is small. And as you can see, same thing happens to the closeness itself. So there is a big difference between gamblers and ransom and random groups themselves. The last one I look at is a centrality. If you look at a network, which are the most central point, and that's called coreness. And coreness wise, that gamblers are really at edges. They are not really central. Gamblers are just basically dealing with only their own cartels. They're not having a lot of other places their money is coming and so on and so forth. Consequently, their coreness, they are at the edges, and therefore coreness is much smaller compared to the others. And same thing happens in terms of cluster coefficients. So basically, I'm just pointing out that all of this really features seem to be very reasonable. I just wanted to point out to you that. Now we're going to use supervised learning approach in terms of identifying ransomware actors. So what we did was interesting. So we have got basically, we look at ego1 graph, ego2 graph, ego3 graph, and the simpler version of that, where we remove multiplicity and loop. So we got basically 6 data sets. And then what we did was for each of the data set, we applied a number of classifiers. So here are the list of classifiers: naive, Bayes, random forest, gradient boosting, and so on. So each of them would produce some sort of classification result here itself. I'm just trying to describe the whole model and give you a perspective of the whole model here itself. Now, obviously, some of the classifiers would do well on certain actors, and some of them will do well on other actors. So clearly, they're all producing results which are not exactly identical, obviously. And some of them might do well for certain kind of graphs, and others might do well for other kind of graphs. So what we do is now we combine them and create a meta learner, which is called stacking. So basically, we're combining each of this gives a certain probability, and we run another model on top of it. That's called stacking. And once we have stacking, then we get stack probability for each of the data set. Now we have got 6 data sets here: ego1 simple, ego2 simple, and so on. So now we got stacking model, which comes out with the corresponding probability. And then finally, we use bagging kind of approach. And bagging is where we are really combining these different outcomes which are coming out, and we are combining them in terms of one data set. And that's nothing but giving a final meta classifier. And that would give you a final prediction. So this is a sort of something which has not been commonly done. And this is another novelty of our approach itself. I'll just now go through some results here itself. So what we do is, as I mentioned to you, individual classifiers, and this is nothing but for ego1 simple, ego1, and these are nothing but the accuracy here itself. And this is only on training data with 5-fold cross-validation on training data here itself. And as you can see, the numbers are not very impressive, somewhere going anywhere from 0.4 to something like around 0.7 here itself. But now we can, obviously some of them are doing better on some sets of graphs. So we are combining them by stacking them. So when we do combine and stack them, again on the training data, you can see the results have been substantially improved. And this is nothing but accuracy, precision, and recall. And now, finally, we have got these 6 sets of data sets. So we combine them, the final result, which is nothing but our final meta classifier, and the results are here. So cross-validated accuracy, precision, and recall all are 1. And on test data set, which we have not used any of this model, all these models were derived for training data. And for the test data set, we're getting almost 85% accuracy, which is unheard of. So the approach has been very, very successful. And here is a confusion matrix I just wanted to show you. And you can read about that again in the paper itself. So in summary and conclusion, let me just mention that really this paper has taken a long time, and it has been interplay between Bitcoin architecture, graph theory, and machine learning here itself. And one of the finding which we had was that detecting ransomware actor can be done using only local clustering and newer methods of machine learning here itself. Results have been impressive in differentiating ransomware actors, gambling actors, and random actors. And obviously there is interesting extensions of this. We need to extend this to what are known as dark web, the one where lots of other things are happening through Tor network. And we want to extend to Tor. We also have to worry about the size of local window. We just looked at plus or minus 1 day. Should it be more or less? We need to also assess how good is our clustering algorithm. Here it did well, but we would like to improve that further so we can get more accuracy out of this. And finally, we want to extend this to other cryptocurrencies. So with that, I'm just going to stop. And if there are